In this video, we look at dependent and independent events. If two events have no effect on each other, they're said to be independent. So here's an example of two independent events. We're going to look at a game that consists of rolling a die, standard six-sided die, and then cutting a deck of cards. The result on the die doesn't impact the result in the cards, and vice versa. So that's why we call these events independent. Just for ease of this example, I'm going to call this event A, the 6 being rolled, and we'll call the 6 being cut event B. So let's look at the probability of A happening. So the probability of getting a 6, there's only one 6 on the die out of 6 possibilities. Let's look at the probability of B happening. So if we're going to cut a 6 from a deck of cards, cutting a 6, there are 4 6s in the deck of 52 cards. And we could reduce that to 1/13. Divide the top and the bottom by 4, and we get 1 out of 13. Well, if we want to find the probability of A and B, what we have to do here is we have to multiply these two probabilities together. We want the probability of this event and this event. They're totally independent. They have no impact on each other, so we just need to multiply those two probabilities together. So 1/6 times 1/13. Remember, when you're multiplying fractions, multiply the numerators together and then multiply the denominators together. So 1 times 1 is 1. 6 times 13 works out to 78. So we get the probability of rolling a 6 and cutting a 6 is 1/78. So therefore, the probability is 1 out of 78. So that was for independent events, and it turns out that for independent events, the probability of A and B happening is always equal to the probability of A times the probability of B. Let's look now at what happens when we have dependent events, two events that are dependent. So if one event has an impact on the other, then we say that the two events are dependent. The way that we calculate the probability of two events happening, so this same idea as before, we're trying to find the probability that A and B happens. Well, that's just equal to the probability that A happens multiplied by the probability that B happens given that A has already happened. It looks a little bit confusing, but we'll go through an example and hopefully it'll make a little sense. This little symbol here just reads given. So let's just jot that down. So this is the probability that B happens given that A has already happened. So here's an example. What is the probability of selecting an ace from a deck of cards followed by a queen? So you pull out an ace, probability of getting an ace, pulling out another card, and having it be a queen. The result here for pulling the queen out is going to be different for the ace because you've already pulled one card out of the deck. So let's walk through this and see what happens. We want to know what's the probability of pulling an ace and a queen. So we'll make the ace event A and the queen event B. So we want to know the probability of A and B. And that's just going to equal the probability of A times the probability of B given A. Well, the probability of A is easy to find. So the probability of getting an ace, and maybe we'll just do that off on the side here. So the probability of getting an ace, there are 4 aces in the deck, 52 cards, so the probability of getting an ace is 4 out of 52, or 1 out of 13. Now the harder part might seem like finding this probability of B given A. So the probability of B given A in this case is the probability that we get a queen given that the first card out was already an ace. Well, if we've already got a card out of the deck, we're not drawing from 52 cards anymore. We're drawing from 51 cards. And we're looking for the number of queens. Well, there are still 4 queens in the deck. So there are 4 ways out of 51 now to get a queen, given that we've already pulled an ace out of the deck of cards. So now we can just plug that into the equation. So the probability of A is 1/13. Probability of B is 4 over 51. And then we just multiply, like we did before, multiply the numerators together, multiply the denominators together, and we get a result of, I guess that's going to be 4 over 663. So the probability of getting an ace followed by a queen is 4 out of 663. So therefore, we can write our conclusion in here and go from there. So let's look at a slightly different example. Again, dealing with dependent events, but a slightly different approach here. So the question is asking, what is the probability of rolling a sum greater than 7? So what's the probability of rolling a sum greater than 7 if you roll 2 dice and the first is a 3? So in this case, we already know that the first die was a 3. So these things become dependent because we're trying to figure out the sum if we already know the result of one of the other dice. So we're going to walk through this here. So we'll call this A here, this first die being a 3. We'll call that our event A. So the probability of A is, our first die is going to be a 3, so that happens 1 way out of 6. Now the other piece of information that we know here in this question is it's asking us, what the probability of rolling a sum greater than 7. So we want a sum greater than 7 given that our first is a 3. So really what this question is actually asking us to find was this part of the equation right up here, this part right up here. So that's what we're trying to find. It's the probability of B given A. So our B then has to be this sum greater than 7. This is what we don't know. But we can find, see if I can get my pen in the right spot, we can find the probability of A and B. So the probability of A and B, if we find that, that'll give us this part of the equation. We'll have this part, and then we can find the probability of B given A. So that's a little bit different in terms of what we're finding, but we can still manage and go about things here. So the question here that we need to find is, what's the probability of getting a 3 and getting a sum greater than 7? So we get a 3, maybe over off on the side here. Well, if our first die is a 3, we could get a 1, a 2, a 3, 4, 5, or a 6 on our second die. So the probability of getting a 3 on the first die and a sum greater than 7, well, a sum greater than 7 means that our second die has to be a 5 or a 6. So there are 2 possibilities for a 3 followed by a sum greater than 7 out of 36 in total. And now we can just use the formula for the probability formula that's listed up above on the top of the page. So the probability of A and B is equal to the probability of A times the probability of B given A. And we can substitute the values that we have and solve the equation for the value that we don't have. So we just figured out that the probability of A and B is 2 out of 36. The probability of A is 1/6. And we want to find the probability of B given A. So now we just need to solve this equation. And we can do that by dividing both sides of the equation by 1/6. So we get 2 over 36 divided by 1/6. And that's equal to the probability of B given A. Remember, when we divide fractions, we multiply by the reciprocal, so we get 2/36 times 6/1. And then we can multiply and reduce. So 2 times 6 is 12/36. I'll just finish this up over here since I'm running out of space. And we can reduce our fraction there to divide top and bottom by 12, and we get 1/3. So the probability of rolling a sum greater than 7, if your first die is a 3, then is 1/3. We can write a little statement here saying that. And yeah, that's how we can use the formula for dependent events to calculate probabilities. So the other option would be to look at actually listing the outcomes, kind of like we did over here. So we looked at all of the outcomes here. Probability of getting a sum of 7 if you know that your first die is a 3. Well, there are only 2 options here out of a total of 2 options out of a total of 6. So there were only 6 options that we had here, and 2 out of those 6 give us what we want. So the probability, if we wanted to look at all the outcomes, probability of B given A is equal to 2/6, which is also equal to 1/3. 2 different ways to do the problem. The way of listing them was a little bit shorter, in this case because there weren't so many outcomes, but if you were dealing with lots of outcomes, that way becomes very tedious. So there's a quick summary: independent and dependent events.